you to at least spend half an hour doing some hands-on practice. So, so this is again the same Docker uh, container loaded in from yesterday, and we have the folder we would open today is Winter School PTA, which is pointer analysis, right? So now, before we dive deep here, I want to just revisit the way Java programs are translated. You know that if you compile Java programs, you get a class file for each class present in a Java file, right? Now what happens in these class files is something we can see. It's possible to see them. They are very human readable. That's one thing I wanted to point out. Do you remember what kind of a machine is a JVM? We had said it's a stack machine. What do we mean by a stack machine? All operations are performed on a stack. Before I go deeper, do you remember postfix evaluation from your data structure courses? Right? What do you do when you evaluate something, some postfix expression using a stack? Yeah, whenever you see an operation, you pop operands, you perform the operation, you push the result back onto the stack. The JVM is a stack machine of exactly the same form. Okay, it evaluates expressions and keeps on putting the results on the stack. At the end of execution of a function or interpretation of a function, the result of evaluating that function is left on the stack. Okay, so that's how a JVM operates, and that basically motivates the design of Java bytecode. So why I want to show some of these things is multiple of you asked about the reasoning behind Java bytecode, for example. So some of you said, oh, why couldn't I have used that as my intermediate representation? What was the question? Whoever asked that question, can you repeat it? Somebody asked in the morning about, yeah. Yeah, sure, sure. So why not treat bytecode as the intermediate representation? It's portable. Well, there are intermediate representations in the compiler, but bytecode was created for two reasons. It was portable, it's platform independent, and yeah, the question she had asked was, oh, usually all compiler IRs are platform independent, isn't it? 3 address code is also platform independent in some sense. So there is an interesting thing why they came up with bytecode. Do you know when did Java become popular? Which year, around what time? 90s, okay, early 90s, early and late 90s, and that was the time when internet had come in. Okay, how many of you have used a dial-up router, dial-up modem? No, none of you. I have used it. It's like 37 kbps used to be the max speed. I think you will die now if you are given such a system and asked to work with it now. But BSNL will give, when broadband came for the first time, data was so expensive. 1 GB of data was, well, before that, this dial-up modem, it will dial the number and connect, and then 37 kbps is the max speed that you would get for opening any website. Secondly, when broadband came in, it was super expensive. This is early 2000s, right? It was super expensive. 1 GB of internet BSNL connection was 250 rupees. In 2000, 250 rupees means today's 1000 rupees roughly. Let's say 750 or 1000 rupees. Internet is the only thing which has got cheaper over the last few decades, right? Now it's almost free. 10 rupees per GB, 20 rupees per GB, and so on. So that was the time we are talking about. In late 90s or early 2000s, internet was super expensive, and internet was becoming very popular, which means people always wanted to write programs that they could run on each other's computer. Now suddenly they could transfer them over the network, and they want people to use run those programs locally on their systems. They want to transfer this by consuming data, which was super expensive and super slow both. So now you wanted any language that was released at that time with the claim that we have code that can be transferred over the internet at less cost, it's small enough, it's secure, and it's cheap, will become popular. And Java came at the right exact time. Okay, so the reason for Java's popularity has many reasons, but one of the reasons, or one of the primary reasons, was its timing. The timing was perfect. Java bytecode became popular suddenly, that, oh fine, we have internet which is costly and we want to transfer code here and there on we run them on browsers. Mobile phones came in at the same time. All initial Snake game and all were written in Java in the older mobile phones. So all of this came at the same time, and people wanted a language which offers portability without being too heavy on the pocket. Okay, so that's one reason some of you asked. So I wanted to just show you some bytecode and show you that it's really small. Let's see, test case all. Does it have some interesting Java programs? Test.java. Oh, this is an interesting program. There is nothing here. Wait, I have some demos. Let me go there. Yeah, our monkey program will work. Okay, so let's open this class once more and let's uncomment some of this so that we have some interesting code here. Okay, and we have this class animal which has two methods and monkey which has one method tail and so on. So forget about the content of the class, let's just look at the structure. So if you compile this file, we had seen yesterday that you would get a dot class for file for each of them. Now there is a command called as java p. Okay, this is the Java disassembler. If you say java p and -c and supply the name of a class, let's say monkey. Okay, it will give you the bytecode of that class and see how compact it is. You have operations like this. Let's see, what does the tail or what does the constructor of the monkey class do? The constructor does x equals 20, y equals 20, z equals 20, right? So now let's see how is it represented in bytecode. A load underscore 0 will load this pointer, and then invoke special. Invoke means call. It's calling, it clearly tells here method animal dot init. What might be an init method? The constructor. So it calls the superclass constructor, as we had said. In fact, looking at bytecode is very helpful to understand the semantics of program at a lower level. We had said there is an implicit call to the superclass constructor. You can see that call over here. And afterwards, you again load this pointer. You have pushed a byte. By push means byte integer. You are pushing an integer byte on the stack. As I reminded you about postfix evaluation, you are pushing an integer byte 20 on the stack. Then you put field. So whatever is at the top of the stack, you are storing into the field. Which field? Field x. So this is basically doing x equals 20. Then you again load this pointer. Then you push the byte 20. This dot field y. This dot y, you are pushing 20 over there. Then again load this pointer. Push the byte 20. Put field z. So number 16 is the index to the field z. It's stored in a place called as constant pool. But here the comment is telling you that number 16 refers to z. So you are storing 20 into this, which is also on the stack. This dot z gets 20. Okay, and then you return. Since the constructor is a void function, basically doesn't return anything particular, so there is a direct return over here. In the next method, so I had promised you I'll at some point of time tell you what is system.out.println. Okay. Many people don't like that in Java writing a hello world program is too long, right? You can't, well, what is the recent Java release? Which is the recent version? 25. So I guess in 24 they came up with this notion of, they have come up with some syntactic sugar on top of Java. So finally hello world programs in Java can be like Python programs. They can be small, but they are just syntactic sugar. Internally they still have a public static void main string args and system.out.println hello world and so on. Okay. So if you want to understand why is this system.out.println written like this, why is not written like just println or just print and so on? Remember, in Java everything is inside a class, and the name of a class starts with a capital letter by convention. Okay, so this system starts with a capital letter, which means system is a class. Now inside a class, ideally you cannot refer to anything inside a class. You have to create an object of that class and then refer to the fields or methods of that class. But if there is a static field in a class, it can be referred to with the class name. Static field means it doesn't belong to any object. It's a global variable kind of a thing. So you can directly refer to static fields of a class by dereferencing the class name. So when you say system.out, it should tell you that out is a field in the class system. Out is a static field in the class system. Now, the field will also have a type, right? In a class, in the class system, I have a field out, but with some type. When I do println, this is a method call. It's clear that it's a method call, right? Println is a method to which I am supplying some arguments here, which is animals tail over here. So println is a method where should that method be declared? Can you read the syntax and just tell? Yeah, in outs class. So out is a field with a certain type. That type is essentially represented by a class, and that class has a method called as println. That's what you are calling right now here. System is a globally available class. Dot out will give you a field. That field class has a method called as println. So this is how it works, and now you can actually see it by looking at the bytecode. What is happening here? Get static, there is a static field called as out whose type is which is in the class Java lang system. You are getting that static field, and the type of that field is java.io.printstream. It's a print stream field. Then you load a constant here. That constant is basically the string monkey's tail as given to you by the comment here. So you load a constant that you want to pass to this. It's a string literal, it's a constant that you want to pass to this println method. So you push it on the stack. Then you invoke virtual. You are calling a virtual method, okay, which is essentially the java.io.printstream classes println method. You are passing that string to it as an argument, and you are returning from here, right? So you can understand quite a bit. When you understand compiler IRs, you can understand quite a bit about the language's semantics, because whenever you lower from a high level to a lower level, you would make a lot of semantics explicit. In this case, you can understand how does system.out.println work, for example, here. All right. So Java P minus C you can use on any class to visualize the bytecode of each class. Let's say I do animal here. It will give me the bytecode of each method, tail method, sound method, the constructor, as well as declaration of the fields here. It does not just store this. The class file stores many other things. If you see Java P minus V, which is a verbose flag, then you can get many more things. It stores some bootstrap methods, inner classes, information about line numbers, which line number maps to what line number of this bytecode, and it also contains variable name mappings and so on. So it contains lots of additional information, flags that tell what field is public, private, protected, and so on, and all of that is stored in a class file which you can visualize by using this command called as Java P. Okay, so that's one thing. So Java programs are converted into this platform independent popular representation called as bytecode. Now you would hear about, when you work with compilers, you would hear about frameworks for writing analysis and optimization passes for a compiler. How many of you have heard about LLVM? Right, all of you I assume. LLVM is a popular compiler or program analysis and optimization framework for C-like programs. You convert C, C++ and many other languages to LLVM IR, and then what is a framework then? So it converts to an IR, but then what's the framework? Similarly, here we would use a framework called as Suit. Suit is a popular program analysis and optimization framework for Java-like programs, or Java bytecode basically. So any language that's converted to Java bytecode can be actually converted to Suit's IR, which is called Gimple. One of you asked me about GCC's IR, which is Gimple. Well, Java has a popular framework used by people which is Suit, and that has Gimple. Okay, so each of these frameworks comes with one or more intermediate representations, but it also comes with various APIs or tools for you to help you write program analysis and transformation. Okay, so that's what we would use, or at least one of them we'll see today. If you have learned, if you have some experience with, let's say, Suit, and then you want to switch to LLVM or vice versa, it's not really difficult. You just need to understand the documentation of that framework. What APIs does it provide to access control flow graph, to access the metadata of an object, to access, given a statement A equals B plus C, how do you take out A from here, B from here, C from here, plus from there, and so on. So there are APIs provided by the framework to do all of this. There are also APIs provided to transform the code, perform data flow analysis, specify data flow functions in some concise manner, for example, and so on. That's the purpose of a program analysis or optimization framework. Is that clear? So what Suite does, for example, is, which is what you see here, this code is written in Suite. So if you see here this pa2.java, point recorder.java, everything inside this winter school PTA folder is written using the Suite framework, which, as I told you, is a popular program analysis framework for Java bytecode. Is Java bytecode the default format only for Java or for any other language as well? This course is not about Java, right? You should know why is it general enough. But not Java bytecode. Yeah, so bytecode is popular. Many languages convert their, many compilers convert input code to some bytecode format for a stack machine. Python bytecode is different from Java bytecode, but there are languages that basically use Java virtual machine to run their code other than Java. Kotlin, yes, yes, good example. More? Dart, yes, yes. More? Some more popular language? Scala, have you heard of Scala or Scala? Yeah. Scala programs are translated to Java bytecode and directly executed on Java virtual machine. There is another language called as Clojure, which is a very functional language. Clojure programs are also translated to Java bytecode, and you can decide to convert any program to Java bytecode and take advantage of the Java virtual machine as the backend, right? So that's the idea of having a separation between front and backend here. So Suite can be used to analyze and optimize any language's program if you can convert that program to Java bytecode. Okay. What does Suite do? It takes Java bytecode as input, converts it into its intermediate representation Jimple, which is a 3-address like code. It converts it into a 3-address kind of format, which looks like Java itself, just that 3-address. Each statement will have only one new a.f.g equal to b will be broken if into temporary equal to a.f, then temporary.g equal to b, and so on. So like this you would break it down into 3-address code, and then it provides you APIs to write data flow analysis and optimizations, and even non-data flow analysis, any transformations and so on the Jimple code. So learning Suite is not possible in 1 hour or 2 hours, but again this is a code base that will give you with some idea about what does it do, and you can use it to play around and learn more in future. Okay. And of course you would find that if you learn one program analysis framework, it's easy to switch to another framework without much difficulty. So here what my exit.sh does is, like yesterday it deletes some class files and everything, then it compiles the code, and then it includes Suite, which is essentially a jar file, in the class path, and calls this class pa2. Pa2 is my assignment over here, assignment which implements pointer analysis in this case. And if you go to pa2.java, there are some arguments passed here, and finally you invoke Suite. When you say Suite.main.main, you are actually calling Suite with those arguments. The arguments are simple. It says, oh, the main class's name is test. The location of the main class and all other classes that I want to analyze, Java code input, is in process dir. What is process dir? It's dir. What is dir? It's the folder test case. So it just says that anything that's inside this folder test case is my input program, and the main class's name is test.java. And once you do that, I think here it's test1, right? Yeah, so let's rename it to test1 here. In pa2, let me call it test1. The main class's name is test1, and with that I invoke Suite. Now what have I done here? Whenever you use a program analysis framework like this, you write a new pass. See, the framework already performs certain passes, right? It's reading Java bytecode, converting it into Jimple. It will also, in this case, Suite also gives you a control flow graph. You don't have to construct it by yourselves. It constructs a control flow graph for Jimple code and gives it to you, along with methods to access the control flow graph, to get the successor of a statement, the predecessor of a statement, to find out if there is a package here, what part is inside a loop, and all of these utilities are provided to you. So Suite does some passes on your input code, constructs some data structures that may be useful to you, for example. It also performs some simple optimizations like constant propagation. And now if you want to do something new like pointer analysis on it, you will have to create your new pass and add to Suite. add to the list of passes that are executed on the input program. If you use LLVM, you will do the same thing. You'll write a new pass, you will add it to a list of passes that's executed when you invoke LLVM on a given program, and it will basically run your pass along with other passes so that all the results are all the results that you expect are achievable. Anyway, so here we have an analysis transformer here, which I am adding to a pack. If you see, there is a pack manager or something which gets, which stores all the passes or packs as Suit calls it, and you are adding your analysis transformer object, which is an object of the class analysis transformer, to this pack. It's just some syntax of adding your analysis pass to the list of passes run by Suit. Okay. Now let's look inside this analysis transformer. Here you can see it basically has a method. Yeah, so this internal transform method is the first method. It's like the main method here. This is the method that's called, and in that you are writing this points to analysis. You can go into points to analysis to understand how does it work, but you're constructing pointer analysis results and printing them in some format like you would see right now in the HTML output. Okay. If at all you want to go inside, let's say there is a points to graph class here that's implementing a points to graph, for example. Now in the points to graph, as we have said, we had nodes and edges. Somebody was asking about how do we clone a points to graph, so we have overridden the clone method here because you want to create copies from inset to outset and so on. So all those things are implemented here. Let's see some interesting one. Let's just take one example just to make sure. Yeah, so let's say I have a copy statement, handle copy statement, very well named method by the student here to handle a copy statement. We have seen copy statement looks like A equals B, right? And now they have written some code such that stack.get stackvar1.clear. So the left hand side, whatever it was pointing to, they have cleared it away. They have killed that information. And then they have said stack.get stackvar1.addall stack.get stackvar2. So this stack, what is this stack? Let's see if it redirects to its definition. It might be declared at the top somewhere. Yeah, so stack is a hash map here. We had said we have a key value pair, right? What was the key in stack? In our stack map, what was the key? The name of a variable. And what is the value? Set of objects that you want to point to. So that's what it is. It's a map here. They have implemented objects also as strings, which is not a good idea, but this was just for a courses assignment. Strings are expensive to work with, so you ideally, well, variable name, you have to keep it as a string, but maybe for an object instead of a string, you could have created some special node that stores the type of the object or something like that, right? So you could have created a separate class instead of storing the name of the object OL or whatever in a string. Okay? But they have done it like this, and this is a valid implementation. So this is a stack map, and this is the heap map as we had seen. It's a two-level hash map. At the first level, you have the object, and then you have a field, and then you have a set of points to elements again. Again, instead of string, if you want to implement it efficiently, I would like you to create a class to represent the field and store it instead of storing the name of the field as a string and so on. So Suit provides such data structures to you already. And then let's go back to the place where we were, handle copy statement. Yeah, what we are doing is we cleared the stack, the points to set of the left hand side variable, and then we added all of the elements that we get by indexing the stack map for stack variable 2. So stack var1 equal to stack var2. This is the statement here. You got all the pointies of stack var2 and added them to the points to set of stack var1 after clearing them in the previous line. So if you go over this code, you would find that this is more or less a faithful implementation of the data flow functions that we have seen for pointer analysis in previous sessions. Okay, and then it will print, as I said, it will print the points to graph in a format that you can study. Now I also told you Suit converts Java bytecode to Jimple, right? You can see Jimple as well. In pa2.java there is an argument here -fj. If you say -fj, it saves Jimple output in a folder called as Suit output. It will come here when we run this file. When we run the exec.sh file, and we would be able to see Jimple code. So see, you are able to see so many things now. You know how to How to see Java code, of course, you understand it. You know how to see bytecode. You would be able to see Jimple code in suit, and this is an example of performing an iterative data flow analysis over Jimple code. All right. So let's just run the exec.sh file which was here. Let's get into a terminal. Student winter school pta bash exec.sh. It ran everything, and you see suddenly a suit output folder has appeared here and a recording folder like yesterday. So so first what you should do is understand Jimple a bit by going to write small Java programs, modify this test1.java after this, and keep adding some constructs to the Java program. Observe how is it converted to 3 address code in this Jimple format. So let's see, test1.java was this. Oh, it's a reasonably complex program. Let's look at a small method here, this one, bar. In bar, you allocate an object of type test1 node and assign it to w. Then you are saying w.f is equal to new test1 node, so one more object. Then you say p2.f is equals w.f. p2 is a parameter here. That object's .f you would point to, you are making it point to w.f. And then system.out.println w, you are printing w, whatever it is. Okay. Let's look at the Jimple code for this. Which class is this in? This is in class test1 itself. So let's go to test1.jimple. In test1.jimple init, so this is the constructor, then this is the main method, this is foo. Which one were we looking at? Bar. So this is bar. As you can see, there are some temporary variables. So any variable which has dollar in its name is a temporary variable created by Jimple here, because you may have long constructs that it wants to break down. And you remember we had said the boundary value would be initialization of parameters to some dummy object, for example. So here you can say that it says, oh, p1 is same as parameter 0, p2 is same as parameter 1 of this method. Its type is also written here. And then we have the interesting statements. The first thing that we had done was creating an object of type test1.node and then w.f equal to test1, another object. So let's see here, we create a new object of type test1.node, assign it to some variable stack3, some temporary variable here. Then we invoke its constructor, special invoke. You remember in the bytecode constructor call was invoke special. So Jimple just called it special invoke. Just twisted the words there. Special invoke is a constructor call init method of the test1 node class. Then it says stack4 is equal to new, again the second object here, call its constructor, and we had said w.f is equal to that object. So stack3 dot f, here is your f. It's printing the type of f as well here, but stack3 dot f is equal to stack4. Stack4 is pointing to the second object and you are just storing it into stack1 dot f, and so on. Then p2 dot f is equal to that new object, and then you are calling println here, passing stack3 to println and returning from there, right? So this is a 3 address code. Now what I would like you to do first is take this test1.java, maybe add some, let's take this bar method itself and try to modify it, add some if else condition there in the original Java code, add some loop there, see if loop is represented as it is in Jimple or is it converted to if and go to, like you are used to seeing, right? So find out how is Jimple generated for typical small kinds of programs. You would run bash exec.sh after modifying this. It will give you the Jimple, updated Jimple here that you can see and try to understand it a bit, make sense of it. And once you are done with that, you can go to the recording folder, and again like yesterday, in the recording folder you can invoke this python 3 minus m, tell me if I make a mistake, directory dot, is that it? Okay. So if you open this over here, again for each method in the program you have the option to show recording here. If you go to it, we were in bar, so here this is the points to graph and this is the current statement. It shows you the points to graph after this statement. It is exactly as what we had seen, just that you should understand Jimple, because in original Java program you didn't have this $stack3 variable, $stack4 variable. So it has converted to Jimple, and then the assignment implements points to graph for this. So here, and there is a list of escaping objects as well maintained at the top. Okay. So now P1 equals parameter, we created a dummy node or an outside node here. Let's just keep moving the slider. We process P2 equal to parameter, so P2 is pointing to another outside node. They have even colored these nodes very well, I think. And then, oh, you have a minus one here. So, okay, let me make one change. You might also need to make it. In the, let me kill it 1 second. And in the pa2.java file, uncomment this. Keep line number. See, what was our abstraction for objects? The line number at which they are allocated, right? So I need to pass this argument to suit in order to preserve the line number of the input Java program, so that an object that's allocated at line number 2 is given the name O2. By default, it was giving the name -1 to all of them. That's why we were not able to see them clearly. Now let's go back and just run bash exec.sh again. Yeah, and now if I run the Python server here, open it in the browser, you can see here that if you click on bar, this -1 is only for these statements that were not there in the original Java program, but for others the line number from the Java program has been copied and it's used to construct the points to graph. So let's say you process this statement, stack3 is equal to new test1.node. You can see here that an object O23 got created and stack3 points to it, right? What should happen after the next statement? It's just the constructor call, so nothing should change in the points to graph unless the constructor was doing something interesting. Then you have stack4 is equal to new node, so one more O24 got created and stack4 points to it, and so on. You keep on changing this and keep on seeing the updates in the points to graph. And I think there is a repetition. I observed this yesterday here. It might be some mistake. So what the mistake is, you reach line 26 here, right? The one which is highlighted, then you reach line 27. So this is the points to graph at the end, but then there is something here. It again resets and it allows showing from the first line once more. Maybe they did a fixed point analysis, and then the number of iterations they do on in the fixed point analysis, all of them are being shown here one by one. That's why it's repeating. That's my guess. And then they achieved the fixed point, so there is only a repetition 2 times here. But in this program, since it's a linear program without a loop, you would see that after you process the return and after you go again, you would see the same points to graph being generated. But if your program had loops, if the points to graph will update in second, third iteration and fixed point achievement will take a few more number of iterations, I believe these repeats will give you different points to graphs until you reach the fixed point. Okay? So you can just play with this now, and as I said, I would like you to in fact add some loop in your Gimple program. First add if else, then add some loop in the test.java file, see the Gimple corresponding to it, then make sense of the points to graph for this example as well as your updated example. See how many iterations you need, how does the points to graph get updated. If you don't understand any step here, if at any step you don't understand, oh, why did this edge got created here? Or why do I have this global variable being pointed to by out or something like that? Ask the TAs or me. Okay. So that's it. Start playing with this. What change we did here? We did 2 changes. Remember, we uncommented keep line number because otherwise all the line numbers were -1, and we did one more change. What was it? Test. The main class name was test1. If you give a wrong main class, it will say I could not find the main class or some such error. Okay, that's it. So you have a concrete example of an analysis framework with you, with a concrete implementation of pointer analysis which matches with what we have seen. I would like you to answer a question while you modify the test cases. I would like you to tell me whether it's an intra-procedural pointer analysis or inter-procedural pointer analysis. How will you find that out? Is the implementation given to you intra-procedural or inter-procedural? How can you find that out without looking at the implementation? Insert a call, and if after the call everything starts pointing to some universal set, that means that's intra or inter? Intra. And if it actually points to what happens inside that method, then it's inter. So I would like you to find out whether the implementation you have is intra-procedural or inter-procedural. Is it handling method calls conservatively, or is it incorporating the effect of the method that is called into the caller? All right, so get started and let me know if you have any doubts.